In this lecture, we look at Young's lattice, which happens to be my favorite lattice. So firstly, we start with the definition of an integer partition. An integer partition is a finite, weakly decreasing sequence of positive integers. Lambda equals lambda 1, lambda 2, lambda L, where lambda 1 is greater than or equal to lambda 2, which is greater than or equal to lambda L, which is positive. And we say that lambda is a partition of n if the sum of these lambdas is equal to n. So basically the question is, in how many ways can I divide the number n into smaller numbers? The order in which I write the summands doesn't really matter, so I will always choose a standard notation and write them in weakly decreasing order. Okay, so now given an integer partition, we can talk about its Ferrers graph or Ferrers diagram. Yeah, maybe I'll call it Ferrers diagram of lambda. What you can think of it is, it's also sometimes called the Young diagram, and I'm going to use that to suggest my notation. Why lambda? It's just a set of ordered pairs of positive integers. Is a set of pairs I comma j, where, so here we'll assume that lambda has this standard form, lambda 1 dot dot lambda n. So 1 less than or equal to I less than or equal to L, 1 less than or equal to j less than or equal to lambda I for each I between 1 and L. And we visualize this by drawing these points as dots using sort of the matrix indexing for positioning. So to explain what I mean, suppose I take lambda equals 2 to 1, then I will draw dots in position 1. So y lambda is going to be equal to 1 comma 1, 1 comma 2, 2 comma 1, 2 comma 2, and 3 comma 1. I will draw these points on a grid. So 1 comma 1 will be drawn in the first row and first column of my grid. 1 comma 2 will be drawn in the second column, first row and second column of my grid. 2 comma 1 second row first column, 2 comma 2 second row second column, and 3 comma 1 third row first column. So this is y lambda. Sometimes we replace these dots by boxes, particularly because we like to put numbers inside them. And this is called the Young diagram. Okay, but for now, let's just use this dot notation. So this is your visualization of an integer partition. You have a left justified array of dots with lambda I dots in the ith row. And in general, a diagram is called a Young diagram or a Ferrers graph. A Young diagram or Ferrers diagram is any left justified array of dots such that each row has at most as many dots as the previous one, or as the row above it. And of course, I only allow finite arrays of such dots. And so you can identify, so let's write y for the set of all integer partitions, and using this notation I can identify y with the set of all Ferrers diagrams. Okay, now I'm going to endow this set y with a partial order. Suppose I have two elements, lambda equals lambda 1, lambda L, and mu equals mu 1, mu m. Then I say that lambda is contained in mu if firstly L is less than or equal to m and lambda I is less than or equal to mu I for I going from 1 to n. In terms of Ferrers diagrams, this is saying that the Ferrers diagram of lambda is contained in the Ferrers diagram of mu. So what we've seen here is that this poset is in bijection with a class of subsets. You can think of each Ferrers diagram as a subset of p squared, where p is the set of positive numbers, integers. Which are subsets of p squared. And it turns out that the intersection of two Ferrers diagrams is still a Ferrers diagram, and the union of two Ferrers diagrams is still a Ferrers diagram. And this means that y is a lattice. Let us just compute the join and meet of two elements. For example, if I take lambda equals 2, 2, 1 and mu equals 3, 1, 1, then I can draw the Ferrers diagram. So this one I've already drawn for you before, and for mu the Ferrers diagram looks like this. And if I take the Ferrers diagram of lambda and the Ferrers diagram of mu and take the dots which are in both of them, then this will be, but maybe I should write here, meet. This will have Ferrers diagram, just these 4 dots, which is the partition 2, 1, 1, and that's just the same as taking the minima of the parts of lambda and the parts of mu. And lambda wedge mu is going to be the union of these Ferrers diagrams, and that's 3, 2, 1. And you can do this even if lambda and mu have different number of parts. In that case, the intersection, the number of parts will be the minimum of the number of parts of lambda and mu, and the join, the union, will have the number of parts equal to the maximum of the number of parts of lambda and mu. And therefore, Y is a lattice. This lattice has many interesting combinatorial properties which we will look at later on in this course.